Hello, my name is Steffen Sæle. The article I'll present to you concerns correlating input data of fire simulations to simulation outputs. This study was conducted as part of the master's program at the Western University of Applied Sciences in Haugesund for fire safety engineering. The simulation software used in the study is Fire Dynamics Simulator. I suppose most of you are familiar, at least to some basic degree, to the nature of FDS and similar software. It uses computational fluid dynamics with emphasis on thermally induced flows. It is regarded well documented, highly reliable, and is applied in fields such as engineering, science, and forensics. However, FDS and similar tools often require massive computational resources. One simulation may take days, weeks, or in some cases, even months. Additionally, many different simulations are often needed. A consequence of this may be fewer simulations than preferred being conducted and uncertainties arising in the analysis. This issue of computational cost and uncertainty is addressed in the study by proposing simple formulas for correlating FDS input to its output. Often, output of interest is related to some mass quantity, such as the soot densities, which are relevant for computing visibility distances through smoke in egress routes. Further, the soot densities in egress routes are highly affected by what fuel happens to be chosen to combust in the simulation, whether it be wooden furniture or plastic commodities. I will avoid technicalities, but the mass source term is here assumed to be relatively dominant to the solution of the FDS mass transport equation. Therefore, any change in this term should strongly relate to change in measured mass in a simulation. For the example equation to the right, the ratios of soot production of two simulations A and B are multiplied with the soot density output of simulation B. This gives an estimation of the soot densities of simulation A. This way, one can generate estimations of many simulations performing only one and some additional simple calculations. To test the correlation, a simple setup of a building fire was modeled. In the figure to the right, this model is shown with a fire placed in the large room to the right. Measurements were made in two locations to investigate possible differences in estimation discrepancies due to the distance from the fire, or rather the energy intensity. 15 simulations were conducted in 3 series, giving 5 simulations per series. Simulations in a series differed only in terms of fuel properties, for instance soot yield and chemical composition. Between series, heat release rates were altered. Results generally indicate that decent estimations can be made by use of the correlations. In the graphs shown here, the dots represent values from one simulation with soot density ratios, estimated to simulated, plotted along the vertical axis. As the right side of the equation below suggests, this ratio should ideally equal unity. Values on the horizontal axis are corresponding values of mass production ratios of the simulations, here referred to as correlation factors, beta. First off, you can see that the values on the vertical axis are further away from unity the further away the correlation factor value is from unity. This suggests that greater differences in fuel parameter input between simulations also lead to increased estimation discrepancy. This finding should be expected due to the nonlinear nature of the governing equations and influence of momentum and heat transfer. Another key finding can be read into the downward tilt of the curves from left to right. This tilt is slightly less pronounced for measurements where the energy level is higher. This either by higher heat release rate or by measuring closer to the fire, seeing as the left figure takes values further away. These changing tilts also indicate that the simulation results are closer and further from the base simulation for high and low values of energy, respectively. Overall, the correlation factor proved to be able to reasonably predict the simulation results for the simulations conducted with an average discrepancy of only 3%. This concludes my presentation. If you have any questions or comments, feel free to contact me via email or the conference platform. Thank you for your attention.